Friends, welcome again to the class of machine learning. In the last class, we learned the basics of linear algebra, starting with the four pillars of linear algebra, that is, the scalars, vectors, matrices, and tensors. We also learned certain operations upon these concepts. Today, we will learn further into the concepts of linear algebra. The salient points will be the system of linear equations, identity matrix, inverse of a matrix, singular matrix, and norms with certain definitions of the different norms to be applied in our studies. So, without wasting further time, let us start with the system of linear equations. So, the system of linear equations so as we have already learned about the matrices and vectors, so we have the variables in X and the coefficients as the elements of matrix A and some values on the right hand side of the equations as elements of matrix B. We can compact it and write in matrix form like this. This is vector multiplied with matrix A. So definitely matrix A is m by n matrix. Vector is n by 1. So to show it as a vector, I give the arrow. You can always give the sign of Hadamard product, then the vector B with m by 1 order, that is m elements with m rows and single column. So where A is an element of r power m by n and X is an element of r power n and B is an element of r power m. So A is two-dimensional, vector X and B are one-dimensional. So if we write in expanded form, it will look like this. So we have the matrix A. So we have A11, A1, 2 like this up to, because there are n columns, A1, n. So like this we can have A21, A22 up to A2, n. This will go up to A m, 1, am, 2 up to am, n, m, n. So this will be definitely matrix A of order m by n. So this is having the dot product with the vector X. Then X can be written as, because there are n columns in A, so matrix with the form of a vector, that is X, will have number of rows equal to n. So this should be x1, x2 up to xn. So this is n by 1 and this should be equal to the vector b1, b2 up to bm, because the Hadamard product of A and X will result in a vector which will have m rows and 1 column. So definitely to equate with the right hand side, we should have the vector of same order, that is m by 1, like this. Now let us recap the idea of identity matrix. So as you may be knowing already what is an identity matrix. I'm writing the caption identity matrix. Identity matrix. So an identity matrix may be represented as IN, which has order n. So we have the diagonal elements as 1 and others 0. So this is 1 0 0 like that, 0 and 0 1 0 like that up to 0. This will come up to 0 0 0 up to 1. So this is n by n identity matrix, which is square. So you have n number of columns and n number of rows. So definitely we have the vector x as an element of r power n, which is one-dimensional vector. So if I find the Hadamard product of in with vector x, then because in is identity matrix, so we should have vector x left with us. So later on we will find the applications of this feature or property of identity matrix. So with the help of this, let us find out the solution of this system of linear equations. So I'm writing here solution of the system of linear equations. So this is equations. So this is in compact form ax equal to b. So because I is the identity matrix, so it means if I find the Hadamard product of A inverse with A, this should be equal to In. So with this knowledge, let us find Ax equal to B. Then if I multiply both sides, that is the left multiplication by A inverse, this will give you A vector x equals to A inverse Hadamard product with B. So this A inverse into A will give you In, and this is vector x, and this is A inverse vector B. I can write it like this, which means that identity matrix with Hadamard product of In and x vector Ax will give us directly vector x, and this can be written as A inverse vector B like this. So that is how we can find the solution of Ax equal to B such that x equal to A inverse B, where A should be invertible. So A is invertible only when A is not singular. So let us know what is the meaning of singular matrix. So what is a singular matrix? Let us learn. Singular matrix. So if a square matrix with its columns are linearly dependent, then in that case the matrix will fall in rank, as we have learned earlier in the solution of system of equations, that if in a matrix either it has dependent row or dependent column, then any one row or column can be made 0, so its determinant can be made 0. It means the matrix will fall in rank. So in such a case, a square matrix with linearly dependent column is a singular matrix, and in that case its rank falls and thus the determinant is 0. Hence it is singular. So you can write a line on it. A square matrix with linearly dependent rows or columns is a singular matrix. So I tell you in a simple word, if the determinant of a matrix is 0, then it is singular. So let us go further. Have a brain teaser. When the case of a matrix is such that A is of the order of m by n, that is, A is not a square matrix, how do you find A inverse? If A is not a square matrix, then how do you find A inverse? So keep a thought upon it, then we shall discuss it a little later, maybe in the next class. Otherwise, if A is a square matrix, then A inverse A equal to A inverse equal to I. So if this order is n by n, this is again n by n, so I is of order n. So our next topic of discussion is norms. Most of us in our undergraduate studies know the term norms by spelling NORMS, but exactly what it is, very few of us learned during our undergraduate studies. But in optimization, norms play a vital role, and most of the times we use norms without knowing that we are using norms. So many a times we need to represent a collection of numbers in a single equivalent for the ease of computation. For example, I have several matrices. I want to scale them through some angle, through some point of view. So these matrices can be converted into an equivalent single number by which we can identify these matrices for certain applications. Suppose we need to measure the size of a vector or a function or a matrix, then we need to find out a single equivalent number. If we can define a single non-negative real number, then this number is possibly a candidate to be a norm. I'm repeating, if it can define a single non-negative real number, say for a vector matrix or a function, then this single non-negative real number is possibly a candidate to be a norm. The norms are generally defined on a domain space like Lebesgue space, Hilbert space, Hardy space, etc. These are the region from which a function has to be mapped, and given the region or range where the function has to be resulted as output. So in the present scenario, we will go for learning the norms on the Lebesgue space. So if you want to know about these spaces, kindly refer to the wikipedia.org or any standard book on system norms. For the present, we discuss what is the idea of Lebesgue space. So we can map our norm that we can treat as a function, which will be mapping from a domain space of Lebesgue, that is a finite dimensional real number space, and that is result in a one dimensional space, that also in a single number. So norm is possibly a mapping from domain of real numbers to the domain of real numbers. So before you look into the properties of the norms, let us consider L1 norm, because once we have a definition of L1 norm, we can understand the properties, then we can try to understand what are the other kinds of norms. So we shall start with L1 norm. So let me write the space as Lebesgue space. So this is Lebesgue, Lebesgue space. This is a space of finite dimensional real numbers. So let us speak about the L1 norm. So I can write at SL superscript 1 as L1. So if you have been given a vector from the space, one dimensional space of real numbers with n elements, then L1 norm is defined as there is a special representation for norm. So we write x, then double bar before and after this, then the subscripts 1 equal to sigma I will vary from 1 to n, the absolute value of each element of the vector x. Because whenever we are defining norm, we want to find out the weight of something. So along a number line, suppose there is x-axis and y-axis, so some points can be towards the positive side of the y-axis, some points can be towards the negative side of y-axis. Whatever be the situation, we basically focus on the difference from the axis. So here, suppose some point is along a y-axis plus 2 and the other point is minus 7. So definitely the weight or weightage of minus 7 will be more, even though this is a negative number. So that is why in norms we are interested in the positive number only. So with this definition, let us see what are the different properties to be used while treating norms. So properties, suppose we define fx as a norm. Fx is a norm on a vector x, where x is an element of r power n. So for the ease of simplicity, I am not putting the sign vector, but you should keep in mind that whenever we are using x in machine learning, we are speaking about the vector. So then first property is, if the function norm has value 0, it is definitely meaning that the vector itself is 0. If f at x plus y has to be compared with f at x and f at y, then definitely we will use a triangular inequality. So this is less than equal to f at x, f at y, which is triangular inequality. For all alpha n element of real space, function over alpha x is definitely equal to modulus of alpha and function of x, and this function of x is also positive. Please keep in mind. That is why I have taken alpha separately and kept the modulus operation upon it, so that we understand that we have to consider the positive values only. Moving further, the next important norm is L2 norm, and very frequently used in optimization problems. L2 norm, you will see most of the applications in optimization based on L2 norm. So this is also known as Euclidean norm. So it is the Euclidean distance from the origin to the point represented by the vector x. So again, x is an element of r power n, and L2 norm is defined as, we will write in a standard format of norm like this, equals to, because we will take the modulus of the vector elements, so xi over its all throughout the length of the vector, square it, sum it, then find the square root of the summation. So that will give us the Euclidean norm. So in most of the practical problems, we find out the difference between two outputs and try to minimize it. So we have to find out the norm and minimize the norm. So that is supported by the advanced computer technologies. So that is why norm is very much in use, not only in this decade but for last 4 to 5 decades. Since last 4 to 5 decades, we are very well in using the L2 norm for optimization problems. So next one, we consider the LP norm. So LP norm is a general form of all these norms. So definitely, as the name suggests, the suffix p, and here again summation I, you take modulus of each element, find the pth power, sum it, then find the pth root of the summation. Next concept is of L infinity norm. So this is also very well established, and it is even more popular than L2 norm, but the applications are critical. So for the ease of use, L2 norm is used. Otherwise, if you see from success in application, then infinity norm is superior over L2 norm. So what is infinity norm? We write L infinity norm This is also known as max norm. Max norm. So it will definitely find out the largest magnitude within the vector. So we can find L infinity norm as x infinity equals to maximum over the magnitudes throughout the vector. So we can understand that suppose in a vector we have three elements, say x1, x2, x3, and suppose x3 is modulus is greater than x1 and its modulus is greater than x2. In that case, we have the infinity norm as mod x3. So this is how we find the L infinity norm and make use of it. The next norm we should consider is analogous to L2 norm, but instead of vectors we will work on matrices. So that is called the Frobenius norm. Frobenius norm. Keep in mind that Euclidean norm is used for vector and Frobenius norm is used for matrices. So given a matrix A, so I suppose that it is a two-dimensional matrix m by n, then the Frobenius norm over A is equal to the magnitude of each element ai comma j then squared, then sum it and find the square root of it. So this will give us the Frobenius norm. So these are the basic definitions of norms, and further when we go into the depth of the machine learning, we'll explore certain more concepts and ideas about norms. But before that, in linear algebra itself, we shall explore about further applications of vectors and matrices. So we'll continue our discussion in the next class, but for today we'll close here. So friends, today we learned about the linear system of equations in matrix form and how to operate it, how to find the inverse of a square matrix, the identity matrix, the singular matrix, and the basic type of norms. So if you find this video useful, please subscribe it and press the bell icon for notification. Like this video, and you can send your queries to my email ID machinelearningbasis@gmail.com. Thank you for your patient listening.